Welcome back to Beyond Zero 2022 and to our last session. Those of you that were here this morning heard Linda Cody speak to the two major strategies for recovering the climate, for removing greenhouse gases out of the atmosphere. And those are nature-based solutions and carbon capture, utilization, and storage. We started the day with nature-based solutions, and we're going to end it with carbon capture, utilization, and storage. We've got three panelists for this topic: Sergio Beretta, Ila Gyenge, and Rob Seeley. I'm going to introduce each of them to kick off their presentations, starting with Sergio. So Sergio Beretta joined UBC's Chemical and Biological Engineering Department in 2019, bringing over 25 years of industrial experience on the scale-up, de-risking, and detailed engineering design of novel process technologies, including 15 years working in the design and commissioning of large processing plants worldwide with projects in 4 continents. Elad, it's a pleasure to have you here, and thank you for your time. Over to you.
Thanks, Alex.
I'm sorry.
That's all right. Thanks, Alex, and thanks for having me. So if we can go into the presentation slides, we're going to get going here. Thank you. So I was given 15 minutes to present to you carbon capture, utilization, and storage technology and industry. So I thought that in 15 minutes, about all that I can do is to give you a very, very global view of what CCUS is, the technologies involved, the technologies readiness levels of those technologies, and the cost of using those technologies. That's what I'm going to try to do in 15 minutes. Let's start by introducing what CCUS is. So CCUS is the integration of technologies to do the following: taking CO2 from flue gases or from the air, capturing and concentrating it. That's what carbon capture is. So when somebody tells you they have carbon capture technology, what they're telling you is that they have technology to concentrate the CO2. Once it's concentrated, you need to do something with it. You can either store it, which is the S part of CCUS, or you can use technology to convert it into something, to utilize it, which is the U part of CCUS. So CCUS, when we talk about CCUS, we are talking about this, the integration of technologies to achieve one of these goals. So is CCUS an important part in our fight against global warming? Well, according to the International Energy Agency, by 2070, we're expecting that CCUS will need to handle approximately 7 billion tons of CO2 emissions from us into the environment, put those away. To put that in perspective, today, the emissions are around 40 billion tons of CO2 per year. So yes, by 2070, we are expecting that CCUS will need to handle a big component of our emissions. Now, how can CCUS help the fight against climate change? Well, it can allow us to actually decarbonize hard-to-abate industries. There are industries like the cement industry or the steel industry where emissions are massive and where they have nothing to do with the type of energy they use. Simply, their reactions make CO2 that goes into the environment. These are industries where CCUS can play a role to decrease their footprint. We can use CCUS also to allow for the production of low carbon hydrogen at scale. And we're going to talk about that more later. It allows us to still use our power plants as they are, especially in those places where we don't have renewable resources or renewable power available to us. We can take the emissions from those power plants and put them away. Finally, it's a key area or key set of technologies to enable what's called carbon negative emissions. And we're going to get to that as well. So where are we today with CCUS? Like I said, by 2070, we're expecting that CCUS must be tackling or handling about 7 billion tons of CO2 per year. Where is Canada today? Canada right now is capturing about 5 million tons of CO2 per year and putting that away. To put that in perspective, in Canada, we have, or we are producing, or we are emitting about 672 million tons of CO2 per year. So there's a big gap. We have a long way to go. Okay, let's get to the interesting part of this presentation, which is technologies, the TRL levels, and their costs. TRL levels, before I get into talk about that, technology readiness level. For those that don't understand that, that's a way for industries to say where is the technology in its commercialization path. TRL 1 means I had an idea. TRL 9 means I'm fully commercial. Let's go in the middle. TRL 5 means I had pilot this concept of idea. TRL 7 means I have done it at some significant scale. Okay, keep that in mind as I'm talking through the next few slides. Okay, let's get into the carbon capture. Let's talk about technologies for carbon capture. And again, carbon capture is only about concentrating the CO2. We still have to do something with the CO2 that is coming out of them. In industry, there are many concepts and ideas, but here there are three industrial ways of doing carbon capture. The first one is using absorption and absorption technologies. These are towers where we have a solution that captures the CO2 and it concentrates it. We can also use similar technology to capture CO2 out of the air, and this is what's called direct air capture. Absorption and absorption technology, the first one, is mainly used for capturing CO2 out of flue gases from plants, concrete plants, just refineries, power plants. DAC concentrates or captures CO2 out of the air, takes it and concentrates it. The last technology here is the use of biological capture systems. These are mainly algae reactors. Algae reactors that can take CO2 out of the air, or they can take CO2 out of the flue gas from emissions from industry. Let's talk about the TRL levels. Today, the TRL level of the absorption and absorption system is 9. It's used in many industries. It's already available and commercially used. We can use the systems to capture CO2 and concentrate it with no risk. DAC technologies are at TRL of 7, meaning that there are some systems that have been built on some scale. And biological capture systems, algae reactors, are either at TRL of 7 or 9. 9 for capturing CO2 right out of the air. This is how we make, seaweed today. And the TRL 7 if we want to use them to capture CO2 out of the flue gas of industrial emissions. What about cost? This is what a lot of people ask me. How expensive is to do this? Well, for the case of absorption systems, today we can actually grab 1 ton of CO2 and concentrate it for about $60 to $80. We still need to do something with that CO2. It's concentrated only, and it's about $60 to $80 per ton. DAC, trying to grab CO2 out of the air. Today, grabbing 1 ton of CO2 out of the air and concentrating it before we do something with it costs over $600 per ton, close to $1,000 per ton, with that price expected to come down to about $200 to $400 per ton. In the case of biological systems, you see the algae reactors. Well, if we want to take CO2 out of the air and making seaweed, there's no cost to that. That's how we make seaweed today. It's just we're making money out of that. But if we want to use the technology to capture CO2 out of the flue gas of plants, then we need different reactors, more complex technology, and the cost is much higher, over $1,000 per ton of CO2 that we capture. Okay, so now we have the CO2 concentrated. Let's do something with it. First, we're going to store it away. Okay, that's part of the S out of CCUS. We're going to store it away. In industry, we look into two main ways of capturing the CO2, of storing the CO2. The first one is to mineralize it. This means taking CO2 from an emission source, whatever that is, we concentrate it by using carbon capture, and once it's concentrated, we inject it into concrete, for example, where it gets absorbed into the concrete and it stays there for a long time. It gets stored away. Now, the parts of this concept are all already commercially available. We already use carbon capture to concentrate CO2, and there are many concrete plants that actually inject concentrated CO2 into their concrete. The whole scheme is not being used yet, but if it was used all together, it is expected that the cost of carbon capture and storage this way, of taking 1 ton of CO2 out of the flue gas of a plant and injecting into that concrete where it's going to stay, is between $0 and $70 per ton of CO2. Let's put this in perspective. By 2030, the government of Canada is expecting that the carbon tax will be at $170. So this is much lower than the carbon tax that we are going to have in Canada by 2030. And like I said, this concept is already being used in some parts in cement and concrete plants. Now, another way of storing it is actually to just grab the CO2 from an emission source, concentrate it, and store it underground in geological storage formations. This is being used in many parts of the world today. Canada has 2 of these big facilities, so therefore the TRL level is 9. And there are there are several of these facilities across the world as well. The cost of grabbing the CO2 and putting it away keeps coming down. Today we are about $100 to $150 per ton of CO2. That compares to a tax that is going to be at $170 in 2030. Like I said, it's today being used in Canada and other places of the world. Now, up to that point, we talked about what could be considered carbon neutral technologies. These are technologies where we actually taking CO2, not allowing it going into the air. But what about carbon negative strategies, where we actually go ahead and use DAC to grab CO2 out of the air, and now we put it underground and store it away? Well, this scheme, as it stands, today is at TRL of 7, mainly because the DAC is at TRL of 7. And the approximate cost has been estimated to be, today, if we do it today, over $600 per ton of CO2. But eventually that cost coming down to about $240 to $440 of ton of CO2. Now, a slightly different way of doing this has been proposed, and it's called bioenergy and carbon capture and storage. The concept is such that we take waste biomass from our forest, burn it to make electricity, green electricity in this case. We'll take those emissions of CO2 from the plant, concentrate them, and store them away. Every part of this concept has been tried already industrially. So every part has been tried. So we are at tier level of 9. The whole concept integrated has not been tried yet. But it's estimated that the cost of putting CO2 away from our environment using this idea will be somewhere in the order of $60 to $160 per ton of CO2. That compares to about $170 tax that is coming for carbon in 2030. Okay, I'm going to go to the last part. I have only a few minutes. So now we have the CO2. Instead of putting it away, we're going to convert it into something. We're going to make something useful with it. Now, I have little time, so I'm only going to talk about thermocatalytic conversions and electrochemical reductions for it. But I'm going to start by saying this. Whatever people tell you, CO2 is a molecule that has no energy. If you want to make it useful, you're going to have to put energy into it. And you're going to have to put a lot of energy into it. And the way that people are looking to put energy into it, forget about all the chemistry here. What I want to point to you is what's on red in there, is that most schemes that people are proposing for converting CO2 into something useful is by the addition of hydrogen. So direct conversion or reaction of CO2, which has no energy, to hydrogen, which has energy, to make something useful, or to do the same thing in electrochemical cells. These are special electrochemical cells where the CO2 comes in, electricity goes in, electricity makes hydrogen within the electrochemical cell to then react with CO2 and making something useful. Forget about that. What I want you to get out of this is that we need hydrogen. And for understanding cost, we need to understand the cost of hydrogen. So let me introduce gray hydrogen first, which is how we make hydrogen nowadays using SMR technology, very polluting. The cost of that hydrogen is about $1.2 to $1.4 per kilogram of hydrogen. Now, people are saying, well, let's make green hydrogen. Green hydrogen is about splitting water inside of an electrochemical cell using renewable power. And what comes out of that is green hydrogen with no pollution at a cost of about $4 to $5 per kilogram of hydrogen. Finally, let me introduce blue hydrogen. This is the idea of making hydrogen the way we are making it today, using SMR technology, very polluting. But instead of letting the pollution come up into the environment, we'll grab it and we store it away. That hydrogen is estimated will have a cost of about $2 to $2.5 per kilogram of hydrogen. With this cost of hydrogen, we can now look at the cost of utilization, CO2 utilization. So I'm going to start with thermocatalytic conversions. And this is a scheme that has been proposed by companies and industry, which is taking emissions, the CO2 from emissions, concentrating them, reacting them with hydrogen to make urea. Urea being a fertilizer that is in very high demand around the world. All these parts are at TRL level of 9. We still concentrate, we know how to concentrate the CO2, and we know how to react hydrogen and CO2 to make urea. But look at the cost. If I use green hydrogen, for every ton of CO2 that I put away into the urea, I need to pay about $400 to $500 per ton of CO2. If I use blue hydrogen, which is cheaper, then the cost goes down to $250 to $350 per ton of CO2 that I put away. That compares to about $100 to $150 for storing the CO2 away, and that compares against $170 for the tax rate that we're going to have in 2030. So yes, it is more expensive because we need hydrogen and we need infrastructure to do so. We can do the same thing. The last point that I want to make on here is that even though, yes, it's expensive, industry is looking into it. In fact, there is a plant in Australia that is going to be making 1.2 million tons per year of green urea very soon. We can use the same concept, and instead of making urea, we can make methanol. React CO2 with hydrogen to make methanol. Now, this idea concept is already at TRL of 9, but the cost of it is even higher. For every ton of CO2 that I convert to methanol using green hydrogen, my cost is going to be about $550 to $650 versus $300 to $400 if I use blue hydrogen. Again, much higher than the $100 to $150 that we just if we just store the CO2 away. And this is already being used in Iceland, where there is a 4,000 ton per year methanol plant using this concept. I'm going to skip to the next one because I ran out of time in here. Methane, we can do the same thing. But the point that I want to make is that the more energetic the molecule you're trying to make, methane be more energetic than methanol, and methanol be more energetic than urea, the more expensive will be to put that CO2 away into those chemicals. Okay? So my last slide in here, I'm just going to try with 2 more slides, which is that people now are talking a lot about using electrochemical cells to not needing to make hydrogen by taking the CO2 into these electrochemical cells and converting directly them into methanol and methane and other useful products. Really what they are saying is, I'm going to introduce clean electricity and make the hydrogen within the cell, which then is going to react with the CO2. It's an interesting technology, has potential, but the TRL levels right now are still low, 4 to 5. And their cost of carbon capture and utilization this way is on the order of over $1,000 per ton of CO2 so far. It will come down, but that's where we are. And I think I'm just going to leave it. Just last point that I like to make in here, which is whether you're making green hydrogen or using clean electricity to convert the CO2 into something useful, what you have to bear in mind is the amount of electricity required is massive. If we just want to deal, for example, with the emissions of one cement plant in the province, producing about 1 megaton of CO2 per year of CO2, which is what they do, you will need approximately 10% of all the electric power of the province just to make that conversion. So these conversions look attractive, but they have a cost. And in this cost it requires a lot of electricity. And I'm just going to stop with that in there.
Thank you very much, Sergio, for giving us that overview of carbon capture, utilization, and storage, which sets us up very well for the next speaker. And that's Ila Genge. He's a professor of chemical engineering at the University of British Columbia and founder of Agora Energy Technologies. Agora is the only company developing a groundbreaking battery technology package that directly utilizes the industrially captured CO2 and generates electricity. The floor is yours.
Thank you very much, Alex, for the introduction. Can I have the slides, please? It was extremely welcomed, Dr. Sergio Breretta's presentation. He set up the stage very nicely for me, so I appreciate that. What I would like to do in my presentation is to bring in the renewable energy storage component, and then to show you how can we combine renewable energy storage with carbon dioxide utilization in a new way, probably in a way that not many people have considered before. So before I go into the deep details of my presentation, first and foremost, I would like to acknowledge that UBC and the startup company I co-founded, Agora Energy Technologies, are located on the traditional, ancestral, and unceded territory of the Musqueam people. And we are very grateful for the generosity, and we are hopeful that we can contribute in a positive manner for a cleaner environment and a cleaner and greener future. So let me give you a little bit of a general context in terms of renewable energies and energy storage. So first of all, when we look at primary energy sources, we have an abundance of renewable sources of electricity. And if we look at this graph on the left-hand side, we can see that the solar energy hitting the Earth every year exceeds the total energy reserves that we have in coal, oil, natural gas, and even including uranium for nuclear. So just imagine this, all the solar energy that is hitting the Earth every year is so abundant that the coal, natural gas, oil, and uranium combined does not have that much energy. And in addition to solar, of course, we have biomass, we have wind energy, geothermal, hydro, which is so important here in BC. So we have an abundance of renewable energy sources. So then the question is, what is the problem? Why it's not so easy to transition to renewables? Well, in my opinion, there are two problems. One is that traditionally the cost of renewable energy generation has been high. However, that cost in the past few years has been dropping significantly. So it's no longer a matter of cost of generation. But the second problem is still persistent, and that is energy storage. Because all these renewables, they are intermittent. We all know from our own experiences, the sun is not always shining, the wind is not always blowing. So therefore, we have to store renewable energy. When it comes to energy storage technologies, many different technologies have been considered, but none of them is really ideal at present. So what are some of the major figures of merit? One is the discharge time. We really need long discharge times for energy storage because we don't simply just want to store renewables for an hour or two. We want to store it for days or maybe weeks or even months. And the second component for energy storage is the cost. And there are, as I mentioned, many technologies considered, but this combination of discharge time, storage time, and cost is not where we would like them to be. So let's just simply look at batteries, which are very popular, and battery technologies such as lithium, market-leading technology that is being deployed also for grid-level energy storage. The issue with lithium-ion batteries is the relatively short duration of storage, about 2 to 3 hours, and also the cost. And if I have to give a number, I would place the cost of storage with lithium-ion batteries at around $150 per kilowatt hour. So this is hindering the transition to clean and renewable energy storage, the lack of adequate storage technologies. Just to bring that point home, all these batteries that we are considering for storage, they are metal-based. And there are major problems with the metal and mineral supply chain and price challenges. the prices of metals and minerals really skyrocketed for the past year or so. Lithium prices are around, for battery grade lithium carbonate, around $75,000 per ton. Cobalt, that is another component of lithium-ion batteries, $82,000 per ton. Even zinc, for certain types of zinc batteries that could be used for energy storage, has increased tremendously. So therefore, our idea was, why not utilize carbon dioxide in a battery setting for energy storage? And this is a new idea. And from an economic point of view, as was mentioned also previously, the cost of CO2 capture from industrial emissions is anywhere between $50 to $150 per ton, so orders of magnitude cheaper than metals for batteries. So we have these two challenges to decarbonization. Energy transition requires renewable sources coupled with long duration and cost-effective storage, and mitigation of CO2 emissions again requires cost-effective large-scale solutions. So I'm not going to insist much on the CO2 utilization because it was mentioned in the previous presentation, and definitely there are challenges, and some of the conversion technologies to chemicals, the economics, they do not work out well at present. And therefore, in our approach, we are looking at combining carbon dioxide with energy storage. So we are building batteries that, when they are charging, when the battery stack is charging, would use captured carbon dioxide from an emitter plus electrolyte, and using renewable energy for the charging stage. And here we are generating the chemicals that they are with high energy density that can be stored for long periods of time. And when the battery is discharged and that energy that we built up and we store during the charge stage is needed, then of course we are providing that electricity to the consumer on site and on demand, and also we are generating value-added chemicals, specifically carbonates. So it is also a pathway for carbon dioxide mineralization, because as you can see, the input is carbon dioxide in terms of chemicals, and the output is carbonates or bicarbonates. So I just want to emphasize here some of the metrics. 1 ton of captured CO2, with 1 ton of captured CO2, we could produce 1.6 megawatt hour of electricity. And we are targeting high energy density, long duration storage at a low cost, and also long cycle life. And this is a technology that was invented here in BC, and now it has been patented globally in over 50 countries. So what can we do with this 1 ton of CO2? So you see, as an input, we have 1 ton of CO2, 2.3 megawatt hours of renewable energy. So with a round trip efficiency of around 70 to 80%, we have an output of 1.6 megawatt hours. So what can we do with 1.6 megawatt hour? We can assure the charging of 14 Tesla Model S vehicles, 1 charge per each vehicle, which would mean approximately 8,900 kilometers driven. Also, with 1.6 megawatt hour electricity produced from 1 ton of CO2, we could assure the daily electricity needs of approximately 65 Vancouver households. So how do we integrate our battery technology with a carbon dioxide emitter? So here on the left-hand side, I want you to imagine a cement plant, but we can replace the cement plant with a pulp and paper mill because they are also emitting carbon dioxide. So we have the emitter, let's say a cement plant or a carbon or a pulp and paper mill. The first step will be the capturing and purification of the carbon dioxide, and then that carbon dioxide goes into the battery in the charge cycle of the battery using renewable energy, and it is converted to a high energy density chemical that can be stored. And then when we need the electricity from the battery, then we are producing clean electricity, and in the discharge step, we are converting that carbon dioxide either to sodium carbonate or to sodium bicarbonate. And so the electricity that is produced from this battery can be reused on site at the plant, or it can provide clean electricity to a nearby community. So depends on the electricity needs of the plant and how that can be managed. And what do we do with the carbonate or bicarbonate product? Two things. One is it could be used again on site of the plant for flue gas treatment with a well-established technology. Sodium bicarbonate is used for flue gas treatment, but also we would produce excess of sodium bicarbonate, so it could be sold on the commodity market at a profit anywhere between $280 to $450 per ton, dependent on the purity of the bicarbonate or so on. So this is how we would integrate the battery with the CO2 emitter. So just a few more slides because I'm running out of time. So where we are with our technology commercialization. We started in late 2017 with catalyst discovery. That is a very important fundamental component. And just specifically on the catalyst side, we are very well developed. We have a high TRL level, but on an entire system level, our TRL level on a system level is around 4 at present and moving toward 5. But when it comes to some of the other components like the gas diffusion electrode, there we have a TRL level of 6. But on a technology level, complete technology package level, we are at TRL 4 moving toward 5. So we are building larger and larger functional prototypes. 200 watt prototype is under manufacturing now at the company. 1 kilowatt it will be followed 5 kilowatts, and then we are projecting in 2024 large-scale demonstrations and the JV agreements with battery manufacturers and the pilot deployment in 2025. So the technology has received a number of accolades, and here I would like to highlight the Impact Canada award and actually competition, Impact Canada Charging the Future from Natural Resources Canada, and we were very honored to be selected in that program, and the Keeling Curve Prize 2021 in the carbon capture and utilization stream. And lastly, I would like to thank very much for your attention. And this graph really shows that start in the last decade, really, we managed, unfortunately, to increase the temperature on Earth by about 0.65 centigrade. And throughout history, the temperature increase was about 1.1 degree centigrade. So it's clearly this graph brings home the message that we cannot keep doing this because it will ruin our environment, it will ruin our livelihood, and we have to look for solutions, and we have to act now. Thank you again for your attention.
Thank you very much, Elad. That was a very inspiring presentation. We've learned a lot about new technologies today, and you just introduced us to another one. I'm going to switch now to Rob Seeley. Rob is the president of E3 Merge Consulting and has over 40 years of experience working in the energy industry. The last 20 years focused on sustainability challenges. His leadership on greenhouse gas management for Shell Canada has included the development of the Quest Carbon Capture and Storage project at the Scotford Upgrader, domestic and international nature-based solution projects, and carbon abatement programs for Shell's oil sands assets. Thank you, Rob, for giving us your time today. Over to you.
All right, thanks, Alex. And thank you, everyone, for hanging in there. Last presentation of the day. So I'm going to shift to try and focus a little bit about, or more about, what do we need to do to make this happen in BC? What is the potential in BC for carbon capture, utilization, and storage? I'm going to start a little bit with the chart of the emission profile of British Columbia. There it is. And Sergio has already summarized how we can utilize carbon capture and storage to reduce emissions, whether it's through reducing for industrial facilities that are operating today or for facilities that will be needed tomorrow but that do not have other options. We talked about cement and steel. And of course, blue hydrogen, we've talked a lot about that. And then the negative carbon technologies, such as direct air capture and bioenergy carbon capture and storage. These are the opportunities, and this is where we will deploy it in British Columbia. Now, how much can that be? Where does it fit? Well, there it is, kind of on the chart, a wedge of what the IEA has said is roughly 30% of the emission reductions needed by 2030 and 2050 could come through carbon capture, utilization, and storage. But let's look a little closer at British Columbia and see if that holds true. In British Columbia, we have a reporting system, sophisticated reporting system for all our major industrial facilities. We have over 500 facilities reporting their CO2 emissions. And this map shows roughly where they are, quite a cluster of activities in Northeast BC with our oil and gas activities, and then other clusters in central, southeast, and southwest British Columbia. If you took those 500 facilities and only looked at the ones that were greater than 100,000 tons, you would have a list of maybe less than 30 facilities. And that's where we need to look. And in that list of less than 30, the industrial facilities would be refineries, chemical plants, steel facilities, mining, aluminum smelter, those kinds of things. And those facilities total, for those large facilities, it's about 6.5 million tons for BC. And I believe the potential to capture CCUS by 2035, I'll say, give us roughly 10 years, or 2032, is about 2 to 4 megatons, 2 to 4 million tons. In oil and gas, again, if you look at only the large emitters, the ones that are more than 100,000 tons per year, we have about 13 million megatons per year of oil and gas emissions from a variety of facilities, but I think that would also include methane. But again, carbon capture, roughly 2 to 4 megatons by 2032. So in the next 10 years, we could get. And then we talk about biomass. Now, biomass is a little bit unique in that the pulp mills only report and pay tax on the combustion emissions from natural gas. But they also emit a lot of CO2 from the pulping process, which is from the biomass material. Now, one would argue, and the government views this as carbon neutral, in that the trees absorb the carbon dioxide already, and that same carbon dioxide is being re-emitted to the atmosphere. So it's carbon neutral. It is reported, but it does not go into the 65 million ton total for BC. But it does create a large opportunity for carbon capture and storage in BC. And those are the yellow dots on this chart. And that is 13.4 million tons per year, of which I believe 5 to 10 million tons is possible to capture in the next 10 years. And then the last category is what we call direct air capture. So of course, there's no dot on the map for this because it doesn't exist. But how much of this could we put in place by 2032? I've only put 1 to 2 million tons. I know that Carbon Engineering has a goal of building 70 of these facilities, each of them capturing 1 million tons per year. So that would be 70 million tons by 2035. So this is very conservative. Let's say we would have 1 or 2 of these operating in 10 years. So the total CCS US opportunity then rolls up to between 10 and 20 million tons per year, which is about 15 to 30% of BC's total emissions. So that kind of fits with what the IEA is saying. So where do we put this stuff if we captured it? Well, Sergio talked about the technologies to capture it, so I'm not going to go into that. But I am going to talk about where do we put this stuff. And this is, of course, an illustration of a core sample. And we need to put this stuff deep underground. It needs to go deep into the sedimentary rocks that have been layered on layered and layered over hundreds of millions of years. And we generally want to put it into sedimentary rock that is below the oil and gas formations. We did this in Scotford. We put it in what was called the basal Cambrian sand, which was a layer of porous rock below the oil and gas formations. And so we'll be looking for those kinds of opportunities in British Columbia as well. Now, we do have lots of sedimentary rock in British Columbia, and that's what I'm going to show you next. The sedimentary rock is in light brown, and of course we all know about northeast British Columbia where our natural gas is produced. That's the same sedimentary rock that would have opportunity for storage of CO2. We also have sedimentary rock in central BC, the Chaco Basin, which is probably the next largest area. It's been lightly explored, would still need considerable work to understand, but it is a deep sedimentary rock formation. And the third, maybe largest one, is actually offshore, Queen Charlotte Basin, also a very large sedimentary rock area. Now, there are other smaller basins. I'm not going to speak to them today that are in the southeast and southwest corners of British Columbia as well. The potential for storage in these sedimentary rocks, even what I would call the saline aquifers, which is sedimentary rock with saline water in the pores, is significant. Some early estimates are 10 billion tons of CO2 storage capacity, which is 500 years of storage if you were capturing 20 million tons per year of CO2. So that's a lot of storage. I don't think we're going to be short on storage. However, we do need to de-risk all this storage by understanding where are the fault lines, what are the seismic risks, what kind of cap rock do we have, and layers over top of these storage areas. So all these things need to be explored, and significant additional work needs to be done to understand this storage potential. And that brings us to, well, how do we combine the capture opportunities with the storage opportunities? And of course, what's happening around the world is people are talking about developing CCS or CCUS hubs. We need to build a hub of activity that is essentially shared infrastructure, so multiple facilities can capture their CO2 and store it at a one central or shared sub-storage infrastructure. And so this creates synergies. It's lower risk in terms of cost in developing the storage, lower risk in terms of sharing the subsurface knowledge. It also starts to create synergies between different activities, particularly when we get into the carbon capture and utilization type technologies, where we want to manufacture hydrogen, but we need to store the CO2 if it's blue hydrogen. And similarly, I think the hub idea also is another way to attract government funding. This is what happened in Alberta. We saw them develop their first hub in the Edmonton area, and now they have 3 or 4 carbon capture projects there, and 2 different storage facilities, one saline aquifer and one enhanced oil recovery. So they have a hub going there, but also they had significant government funding to help them get that going. And so we have the potential for 3 or 4 hubs in British Columbia. I was going to give a couple snapshots here on what these hubs might look like. This one is what I call an onshore hub, so it could be northeast BC or central BC. But I think one of the anchor facilities could be a pulp and paper facility where, in fact, this is a negative carbon facility in that we're capturing CO2 that's come from biomass. So the trees have already absorbed the CO2 out of the atmosphere, And now we're going to take that CO2, capture it from the pulp mill stack, and put it back into the ground. We would add in a gas plant with it, perhaps a direct air capture facility, and maybe even a hydrogen manufacturing facility and a methanol facility where we're using carbon capture utilization. This kind of a hub could sequester between 3 and 5 million tons per year. The other hub that I wanted to speak illustratively about is the offshore idea. Now, there is an opportunity to capture CO2 at all our industrial facilities and our pulp mills all along the coast, and then ship those CO2, ship the CO2 to a central onshore receiving terminal, and then from the receiving terminal would go to a subsurface well. Now, what I do know from the Quest project in Alberta, that one of these wells can store up to 1 million tons, sometimes more, 1.5 million tons per year of CO2. So at that rate, we would only need 5 wells to store 5 million tons. So it's not like we have hundreds of wells being drilled on the seabed floor to store CO2. We could isolate the location and have a series of wells that are dedicated for CO2 storage, and use our offshore sedimentary basins for this opportunity. Now in BC, we have a challenge. There is a moratorium on offshore drilling. So I guess we need to ask the question, does that include drilling for CO2 storage, or was that only drilling for oil and gas production? So these are some of the questions that need to be addressed. And of course, we would need to do a deep environmental impact assessment on this kind of a proposal. And there's a whole business of subsurface rights. So there's lots of challenges there, but again, there's a significant opportunity. And then at the last slide and the last piece of my presentation is really what do we need to make this happen? And I would say first it would be a vision for a series of BC industrial CCUS hubs. And I think this needs to come from the BC government. Certainly industry needs to partner in it, and others that are willing and able to put their shoulder behind it. But it needs to likely come from the government initially. And that's what happened in Alberta in order for them to get their first CCS hub going. And the second piece to the puzzle is we need to do more work on the subsurface in terms of understanding the storage facilities. So whether that's seismic work, test well programs, but there's an urgent need to get underneath this and really understand it. So where can we store this CO2 safely and permanently? And then the third thing could be for industry and government partnership, and First Nations for that matter, around the development program for a CCS storage, transportation storage. And I propose that we need some direct funding from the government of BC in this development initiative. And the fourth on the list is an offset system in BC. There's lots of talk about this. We have, but what people need to know is that carbon capture and storage often falls into the category of an offset. And that's because the emissions that are being captured, whether it's a process gas emissions or direct air capture or emission from a bioenergy source such as pulp and paper, these are not regulated emissions. They're not taxed emissions. So there's very little incentive to go and capture them. So if they can qualify as offsets and be used to abate emissions, then it's another way of making this happen. So CCUS as part of the offset system is a very important tool in the toolkit. And then the last piece is all the rules of the game around CCUS. Well, it's protocols for offsets. It's measurement, monitoring, verification for the storage of the CO2, and also around subsurface rights and delineation. So those are the points that I want to make today in the presentation. Be happy to take answers to your questions, and thanks so much to the other speakers for providing all the groundwork for this presentation. Thanks, Alex.
Thank you so much, Rob. That was really interesting as well. And we have time for a few questions. We have one question from the audience for you, Dr. Genge. And then I'd like to ask a question for all three of you to answer. So the specific question about the CO2 battery technology is how much such capacity can be installed without oversupplying the sodium carbonate or bicarbonate markets?
Yes, this is a very good point. And first of all, there is a huge market for sodium carbonates, especially, if I'm not mistaken, it's about something like 50 million tons per year, the sodium carbonate market. And there is a company, Solvay, which is one of the leaders in carbonate production. So the market for carbonate is huge. And I think even if the CO2 battery technology would oversupply the carbonate market, the carbonates could be stored and would, even if they are not utilized in any other industry, would be basically simply stored and as a way to fix and mineralize carbon dioxide. So a short answer to this very good question is that the carbonate market is very large. I don't think that in the next decade or so with the battery technology we could oversupply. But even if it would come to that point in the most optimistic deployment scenario, as an option of last resort, these solid carbonates could be stored safely for long periods of time if they are not used for anything else.
Thank you. Great answer. We have another question just came up. I think this one probably is best directed to you, Rob. And that is CCS in sedimentary rock. Does it factor in the perpetual costs of monitoring, the induced seismicity, transportation costs, and liability in case of leakage?
Yeah, great question. Yes, at this point in time, I know that my experience with the Scotford Quest project, they're injecting the CO2 at 2 kilometers depth into what we call basal Cambrian sand, sandstone rock essentially with porous openings. And with that, yes, the cost of CCS does include the monitoring, measurement, and verification system. In that case, they measure the plume of the CO2 as it's moving along with the basal, the saline aquifer. They have measurements on the surface, also through the whole region for any seismicity and potential CO2 leakage from fault lines. They've been operating there since 2013 and really have had no issues whatsoever with any kinds of leakage or seismicity. What I would like to say is the seismicity is very specific to the geology. So I'm talking about Alberta. If we're talking about other locations, we need to think about that differently and understand that science as well.
Thanks, Rob. Okay, just one last question from the audience I'd like to put out to you, and I'll add a question on and then go to each of you. And the question is, what are the opportunities that you see for First Nations leadership in the CCUS area? And what I want to add to that, starting with you, Sergio, is if you forecast yourself into 2060 and imagine you're looking back in time to 2022, and you're looking back and describing the path that CCUS has followed and how it's helped us achieve what it is we have to achieve, which is not only net zero emissions, but actually negative emissions. Tell us about the path we followed in terms of the highlights. So, role of First Nations, looking back along the path. Over to you, Sergio.
Thank you. I think on the looking at that year 2060 or whatever that far is I see us transitioning from where we are on fossil fuels to renewables be the end goal. But CCUS will be that set of technologies that will help us get there while dealing with global warming issues, with emission issues. What do I see? I see the possibility, which I get pretty excited, is the idea of using a lot of the biomass as one way, one example, is opening the waste biomass of the provinces. As Rob said, keep understanding the geology that we have to deal so that we can start putting some more carbon storage areas in the map, and then be combining the excess of biomass we have in the province, use it for energy, displacing fossil fuels by doing so, and capturing a lot of that CO2 into storage areas that First Nations can take a leadership on finding, on putting in place, on managing, so that us as an industry can start using and just start reducing not just the overall emissions, but getting into carbon negative opportunities. Just being a leader for the rest of the world is that combination of geological storage and the use of the excess of waste biomass we have in the province. I think it presents an incredible opportunities for us to show how it can be done as a transition piece. In the end, I think it comes down to we have to stop using fossil fuels and be reliant on renewables. Now, like we said before, there are some industries that just can't just simply change to renewables. They still have emissions, and those are the ones that will need the storage capacity moving forward. I'm going to say one more thing on that, though, and nothing to do with your question, which is we just have to make sure also that the policies that the governments put in place start closing some of the loopholes that a lot of these industry that are considered critical to the province have, to not having to pay some of the carbon tax that the rest of us pay. It's just making sure there's pressure for all of us, including all the industries, to just start moving towards decarbonization. So policies in place, but I hope that I answer your question on the first part of how CCUS will be critical to get us from here to a future where renewables are the source of energy for us.
Okay, we have a dilemma. We have 2 minutes. Rob, you get one of them.
Okay, yeah, I think in terms of the role First Nations can play in CCS, I think it's a very important role, and I think it's related to the subsurface. So many of the challenges with CCS is about finding the location for storage and then gaining public acceptance for that location to actually do the subsurface storage and develop a subsurface storage facility. So First Nations may want to get involved in, for example, subsurface storage rights and in the whole assurance process of, yeah, this is a good location, or no, this isn't a good location. But with First Nations knowledge and understanding of the storage science and having them behind it, it can play an important role into establishing those locations in British Columbia and Canada.
Great, thanks, Rob. Another minute for you, Elad. Off you go.
Yeah, I think that when it comes to First Nations and each and every First Nations community, they have their own specific issues. And first, it would be excellent to listen to the First Nations experiences with the climate and to see how different technologies could fit into their needs. And there are different technology toolkits, as we could see today in different presentations, but not all of them would fit their needs. So I think it has to be identified which one would be the best solution, what type of industry is nearby, how they could work together with that industry, whether it's a pulp mill or whether it is a cement plant, and and to adopt the right technology, whether it's CCUS or renewable energy storage. And also for me, what is very important is for remotely located communities is to the diesel fuel and to eliminate the reliance on expensive and dirty diesel fuels. And I think that is a very high priority. And again, there are different technology solutions that could be adopted, but it should come through a consultation process with the communities.
Thank you so much, all three of you. You've unpacked a complicated topic for us to the point where even I understood it. So thank you so much. We're going to take a break now for a couple of minutes, and then we're going to move into our closing. Thanks, everyone. You just have to go to the Whova app, and you can take the next link to the closing. Thank you all very much.